For the sake of simplicity, we just take 180 degree, right? Instead of writing plus or minus 180 times 2k plus 1. Then what do you and I get from this equation? Or let's say plus or minus 180 degrees, right? To 2k plus 1. Doesn't matter, right? So we want ST plus P1. So that, how do I get plus or minus 180 times 2k plus 1 minus, if I rearrange the equation, I'll get ST plus P2 plus ST plus P3 plus angle of ST plus Z1. I hope till here I'm clear, because
yes, sir.
Now let's interpret. Okay, so this I will just take as 180, for the sake of calculations. Okay, so you and I can take it as plus or minus 180 or plus or minus what to say 180 times 3 is going to be 540 and so on. Anyway, things are going to be periodic. Okay, so no problem about that, right? So now, what is ST plus P2? Let's zoom in once again. Where is ST? ST is infinitesimally close to this minus P1. So if I draw ST plus P2, angle of ST plus P2 is going to be equal to angle made by a vector drawn from minus P2 to ST. Okay, that's how you and I should interpret. And what is the vector drawn from minus P2 to ST? It is this vector, right? Is it correct? Because it is ST is very close to minus P1. So it is almost the same as drawing a vector from minus P2 to minus P1. Okay. So now I hope you're getting the answer to your question, Vikas, right? So what will be ST plus Z1? Let's figure it out. It will be ST minus or minus Z1. What is this vector? It is the vector drawn from minus Z1 to ST or minus P1, right? So now I hope it's clear how we got it out, right? Sir?
Yes, sir. Clear. Thank you.
Yeah. Yes, sir. Yes, sir. Prem, you had a question? No.
Clear, sir.
Yeah, the questions were on the same lines only.
Same line. Okay. Yeah. So, yeah. All right. So once again, so kindly watch those videos on control systems. I think there I would have gone in depth. So here I'm just only, summarizing the main steps, so that we apply them. But I'm very happy that your batch is asking all these questions. Okay, that shows that's a very positive indicator. Okay, yeah. All right. So, and please keep asking these questions so that I will also remain sharp. Okay, so I should also be able to answer these questions. Okay. All right. So now that we have completed step 5, let's go to this last step, okay, which is what is called as determining the crossover points. Okay, that is, we need to figure out where the root locus may cross the imaginary axis. Now, why is this step important from a practical perspective? Right? Let's figure it out. So, where is this step? Okay. So if we look at this S-plane, we know that this is the left of plane, this is the right of plane, right? And the imaginary axis is the boundary or the stability boundary, right? It separates the left of plane or the right of plane. Now, why do you think the imaginary axis becomes important here? Or why are we worried about the root locus branches? When do they cross the imaginary axis?
Because if it is crossing the imaginary axis, at that point it will become unstable. System might become unstable.
It can, very good. It can go both ways. Right? That is, if I go from LHP to RHP, I need to cut the imaginary axis. Then I will go from stable to unstable. If it's the other way around, I may come from RHP to LHP. So for a physical system, as a design engineer, I need to know if at all there is a case where for some value of this gain k, which may be a controller parameter, am I going to cut the imaginary axis? Okay, then I would be careful, right? Such points where we cut the imaginary axis are what are called crossover points. Okay? So once again, all these terms have a lot of intuition, right? Why do you think it's called crossover?
Because it is moving from stable to unstable zone or vice versa.
It is crossing over from LHP to RHP or vice versa, right? Yeah, that's why it is called crossover point. Okay. So now, how do I figure out the crossover point? Okay. So please note, in general, S is a complex variable which will have the structure of sigma plus j omega. But on the imaginary axis, sigma becomes equal to 0. So S equals j omega characterizes the imaginary axis. Okay, please remember that. This is important for us even when we go to frequency response analysis. Okay? So what we do is that if you and I want to find out these potential crossover points, in the closed loop characteristic equation, 1 plus g of s h of s, we substitute s equals j omega and then like figure out whether there is any potential solution, right, which is reasonable for a crossover point. Okay, so let's do that in this particular example. So for us, if you recall, the closed loop characteristic equation is 1 plus k divided by s squared plus 4s equal to 0. And if we simplify that, we get s squared plus 4s plus k equals 0. So what we do, we substitute s equals j omega. Now, when we substitute s equals j omega, s squared becomes minus omega squared. Why did we get minus omega squared? J squared omega squared, right? J squared is minus omega. So that's how we got minus omega squared. Then we had plus 4j omega plus k. So if we rearrange, we get this. Okay, we combine the real part and the imaginary part. Now, at first glance, one may think, oh, okay, look, I have only one equation, but two unknowns, right? What are the two unknowns? Omega and k. But then it so turns out that, like this equation is a complex equation, right? So when we have a complex equation or complex expression being equal to 0, both the real part is 0 and imaginary part is 0. So that's why we get these two equations, right? So minus omega squared plus k is the real part, that is also 0. 4 omega equals 0, that is also 0. So from the second equation, you and I get omega equals 0 as a potential crossover point. And we substitute into the first equation, k equals 0 is the solution. So what it means is that, how do we interpret it physically? In this particular example, when we plot the root locus, if you recall, there are two open loop ports, right? One at -4 and one at 0. So when k is 0, one branch starts like this, another branch starts like this. So there is only one crossover point. That is, when k is 0, the one branch starts at the origin. Beyond that, the two branches of the root locus never go into the RHP, which is very good result for us, right? That means for every value of k greater than 0, you and I know that the closed loop system is stable. Of course, you and I would have already derived it in stability analysis, but this is we are still figuring out from root locus. I hope this step is clear. Okay, so in this particular example, k equals 0 is the only, or s equals 0 is the only crossover point, and which is where one of the branches starts off. Okay, I hope this step is clear. All right. Okay. So I hope it's clear what is the purpose of calculating the crossover point and what do we interpret from this step. Right? Any questions on that before we put everything together and then we come to the main observation of how the root locus is helpful to us? Okay, so now let's put everything together. We have drawn the root locus plot down, but let me draw it now. Okay, so we know that there are two asymptotes, plus or minus 90 degrees at -2. Coincidentally, -2 is also the breakaway point. Okay, this is a very, very special example. Okay, please note the point of intersection of the asymptotes and breakaway point need not be the same. Okay, in this particular example, they happen to be the same. Okay, so what happens is that one branch starts from here, one branch starts from here. When k equals 4, we have a breakaway point at -2. And then as k tends to infinity, the two branches of the root locus go along the two asymptotes to infinity in the S plane. Okay, so this is the root locus for this particular example. Okay, so please note, when we construct the root locus, you and I need to show what are the limiting values, directions at k equals 0 and k tending to infinity. We should also clearly mark the intersection of asymptotes, breakaway point, break-in point, and the corresponding value of k, and crossover points and the corresponding value of k. Okay, the root locus point. And we should also show these arrows. Okay, the arrows indicate how the root locus, the roots vary as k varies. Okay, that is also an important expectation of a root locus. Okay, this is how we calculate the root locus plot. And now from the root locus, you and I can immediately say that the closed loop system is stable for all k greater than 0. Obviously, we got that result from the Rhodes criteria before itself, right? But you and I can reconfirm it. Why? Because there are two branches in the root locus. For any k greater than 0, where do the two branches of the root locus lie in LHV or RHV? If you look at this graphic,
LHP only, sir.
LHP, right?
Yes,
So,
yes.
please note, each branch of the root locus characterizes one closed loop pole, right? So, if both branches of the root locus lie in the left of complex plane, that means that both the closed loop poles are at the left of complex plane for all k greater than 0. So, that means that the closed loop system is stable for all k greater than 0. Okay, so I hope it's clear how we got to this conclusion from this particular exercise. Okay. Any questions before we go to the last concept for today? All right. So now I made one. Yeah. Yes, please. Any questions?
Sir, this question might be very basic, but
Ah.
why do we have to go along the asymptote when we are going for k greater than k tending to infinity? I'm sorry. To
So
ask this again.
no, that is the definition of the asymptote. Say plane. Okay. Asymptote means you go along the direction. All right. Yeah. That is the definition of asymptote, and that is how we have calculated it. Okay. Yeah.
Because we are going from a pole to a zero, so it has to go along that direction. Am I
So
right? Yeah.
the interpretation is that since there are not enough open loops. See, when do we have asymptotes? Only when m is less than n. So,
Correct.
bottom line is that you and I do not have enough open loops where the branches which start from an open loop, or we don't have enough open loop zeros, right? Where a
Correct.
branch which starts from an open loop pole can end. Okay, so consequently, that is why we are going to infinity along the symptom. See, there is one subtle thing there, Prem. Okay, so once again, why this is along infinity. So once again, if I have to go back and share the subtle notions, let's say I go back to this example, right, which we already looked at. Now, what is the value of n here? N is the
For which example? Oh, this example.
this particular example. Sorry, let me put a box around it. The general one which we calculated for.
Three.
I'm
sir,
sorry.
three, sir.
N is 3 because denominator polynomial is of order 3, right?
Yeah.
Then what is the value of m?
One.
1, right? So if n is 3 and m is 1, right?
M less than n.
Now we have a case m less than n. So obviously, two branches are going to go to infinity along
Asymptote. Yeah.
now, why is this infinity? The subtle point there is the following, right? Just for the sake of argument, right? You and I can write it as 0s plus 1, right? Sorry.
Yeah, it's
0s.
into one.
So just to make the number of factors equal in the denominator and the numerator, I'm just doing this, right? So yeah. Now, at a conceptual level, right? We are having n equal to m, right? So that is, I hope you get the subtle point, right? So that is, we want to ensure that there are as many zeros or as many points where the branches, each of the branches will end, right? So,
Understood, sir.
so for these two things, what is the value of 0? It is as if they are at infinity. That's why they are asymptotes, right? So I hope that subtle point is clear there. Okay. Yeah.
Got it, sir.
Yes, sir.
Yeah. Any other questions?
We can continue, sir.
Okay. All right. So now coming to the last concept. So if you recall, even when we looked at a proportional controller, right? I commented that, okay, look, when we do stability analysis, in this particular problem, we narrowed down, right? From minus infinity to plus infinity. And then we saw that for stability, KP should be between 0 and infinity. Then for performance, we go further down, right? That is where root locus comes in, right, and helps us. So can we narrow it down to a smaller range? So now, if you recall, we constructed settling time less than 4 seconds, peak overshoot less than 10%, right? The corresponding close to pole region required for that, right? So where we want to ensure that the closed loop system satisfy the performance, these two performance requirements. And if you recall, the corresponding open trapezoid was this, right? What I am retracing here, right? Now, if a system needs to satisfy both performance and stability and performance, we already saw that for all k greater than 0, the closed loop system is stable. Okay, so that is understood. But if I want to satisfy performance, what is it that I need to ensure? I need to ensure that both the branches of the root locus in this particular example should lie within this open trapezoid, right? Now, how do I calculate it? So please note that this branch from -4 starts within that trapezoid, but the other branch starting from 0 starts outside the trapezoid, and it comes within the trapezoid only what we label as point A. So I need to find out what is the value of k at point A, right? How do I do that? Once again, we use the closed loop characteristic equation. Okay, so closed loop characteristic equation is the equation that relates the S value of k and closed loop poles, right? From here, we get this formula, right? If I rearrange it, k is minus s squared plus 4s. So if I substitute s equals -1, which is this point, I get k to be 3. So what does this imply? When k is greater than 3, both branches come into the open trapezoid, right, that we have. I hope this step is clear. Okay, please ask me any questions before I move forward. Is this step clear to everyone? We are going step by step. Okay, there are two branches starting, one at 0 and one at -4. The branch starting at -4 is remaining in the initial phases within the open trapezoid, but the branch starting at 0 enters the open trapezoid only when it hits the -1 point, right? As we can see graphically. And so consequently, we found the value of k to be 3 at the -1 point. Okay, when s equals -1 for this particular closed loop system. Okay, using this equation. I hope this is clear. But do the two branches remain within the open trapezoid for all k greater than 3 to infinity?
No.
What happens? When do they go outside the trapezoid?
If the in imaginary axis length is is falling away out of the boundary, like
So
2 10. Okay.
yeah, please go ahead, Roshan.
2 into 10 57.33 degree, beyond that length of the it will go outside of the boundary.
So let me zoom in and explain here. So please note, one branch is coming like this. It hits they intersect at -2, and then both the branches go like this along asymptotes, right? Now, what we have labeled as point B and point C, beyond that, the two branches go outside the trapezoid. That means beyond that, the peak overshoot condition is not satisfied, right? Because we want both settling time and peak overshoot to be satisfied. Is it not? So at points B and C, I'm having the performance condition not being met beyond those 2 points, right? When the root locus branches go outside the trapezoid. So I need to find out what is the value of k at B. For that, I need to find out what is the value of S at B. So say the value of k at B and C will be the same because of symmetry. Okay, because we are dealing with the polynomial with real coefficients. Roots will be complex conjugate. So poles, close to poles are also complex conjugate. So if you find the value of k at B, it will be the same as finding the value of k at C. Okay, that symmetry holds. Okay, please note that B and C are complex conjugate points. So how do I find the value of S at B? So it is going to be, the real part is going to be -2. What is the imaginary part? You look at this right triangle, right? This angle we found to be, oops, sorry, what happened? Oh, sorry about that.
57.33, sir.
This, where it's, yeah, here it is, right? This angle is 53.7. This adjacent side is 2. So this is going to be 2 tan 53.7. Okay, so the value of S at point B is -2, which is the real part, plus 2 times 53.7 times J. Okay, so I'm writing it this way. So that's what you and I do here. So we go and find what is the value of S at B. Then we go and substitute that value of S into this equation for K. We get the value as 11.45. Okay, you may think, hey, look, oh, the value of S is complex. How do we get a real number? Okay, so that's how it is. Okay, so we get a real number for this. All right. So that's how you and I go and calculate this value of K at B. And the value of K at C is going to be the same, okay, as otherwise, right? So essentially, we are going to have, the value of K at the point C is going to be 11.45 also, okay? So what can you and I interpret? That is the performance requirements as given for settling time and peak overshoot as specified by this open trapezoid is satisfied only when both branches of the root locus lie within this open trapezoid. And that happens only when K is greater than 3 but less than 11.45. So you can see that you and I have reduced through this analysis the potential region of K or KP, right, in this particular example, right, where you and I need to go and fine tune from -infinity to +infinity. Using stability analysis, we found that KP should be positive. Then performance analysis and root locus, we even narrowed it down to 3 to 11.45, right? And that is what is shown in this graph, right? The feasible region should be greater than 0 for stability, but then we narrowed it down to 3 to 11.45 for both stability and performance. And I hope this demonstrates the usefulness and the application of the methods that you and I have been learning. Imagine that this is a system for a motor which is being used, let's say, in the steering system or a traction motor and so on, right? We are asked to design a proportional control, right? Then what happens is that we are essentially going to have to tune KP between 3 and 11.45, which is a big relief rather than tuning from -infinity to +infinity, right? So I hope this demonstrates the the application and the usefulness of this particular method.
Sir, I have a question over here. Suppose if I'm not aware of root locus method for finding this range of KP over here or K over here, so I can do this problem in a trivial way that you have taught us in the previous class, that if I express this and compare it with the standard y double dot plus 2 into xi into omega n y dot plus omega n square, and if I compare that coefficients and express the k in terms of xi in terms of k, and then apply the MP formula like e to the power minus pi into xi divided by 1 minus under root 1 minus xi square should be less than 0.1. So by that also we will get the value of k. Is that right, sir?
Please try out, scan the solution and tell me, Roshan. I want you to figure it out yourself, right? Please note, I have only 2 comments which will serve as hints for you for the method that you have proposed. Very good thought process, right? But what will happen is that I have only 2 comments, right? Let's say In this particular example, you and I are dealing with a second order system. But please remember, the performance specifications are derived based on dominant second order systems. So in real life, you may have a fifth order system. Then the method that you are discussing may not work out. Okay, root locus will be more powerful. Okay, point number one. But having said that, let's stick to this second order system. Okay, we have only this particular example. Let's say we are always going to encounter only second order systems in real life. Let's talk with that perspective. What you are proposing is a very nice thought. Please try it out. What you will get is that you will get only the limiting value of k where it hits this thing. Okay, so but then you and I want a range, right? Please note, like all these are approximations of reality erosion, right? See, who said a traction motor or a steering motor should be a linear timing variant, second order underdamped system, right? You and they are approximating it as that, right? So that is why in these methods, we want to get a range of parameters in which you and I will go and tune and then find the best possible value. Okay. So that is the second point I will give as a response to your question. But good thought process. Please try it out. Okay, and show me what you get.
Okay, sir. Thank you so much.
Sir,
Yes, please.
so here, if we see the root locus, means whatever we have drawn in green arrows, so one of the portion of the locus is -4 to 0, -4 to 2.
-4 to -2. Okay.
-4 to -2, yes. So
So,
this portion is entirely into the trapezoid.
yes.
So means how do we interpret that this k0 to k is equal to 4 lies within the stability as well as performance requirements?
So see, because we should not interpret it that way, because see, please note, I'm repeating again, all branches of root locus, the keyword is all. Okay, all branches of the root locus should lie in left off plane for stability. All branches of the root locus must lie in this open trapezoid for performance. Okay, it so happened that, let's say we call this as branch 1. Okay, and this is branch 2. What you are saying is that, look, hey, you know what, the portion of branch 1 on the real axis always within this open trapezoid, right? Does it mean that it satisfies performance completely? No, because why? One half of branch 2 lies outside the open trapezoid. Okay, that is why we figured out k greater than 3 as one limit. I hope that answers the question.
Yes, thank you.
Okay? Yeah. Oh, okay, I think it's almost 5:55. Arnachalam, is everyone present today? No, sir.
Sir, only one absent, sir. Hemant.
Hemant alone is absent. Okay, so everyone else is present. Is it? Hello? Okay, yeah, I'll mark attendance there for everyone. So we will continue from here. Okay, so if there are more questions also, we can continue from here. In tomorrow's class, we look at what happens with positive feedback. We will learn what are the complementary steps. Then I will give you homework problems also, through which you can do things and then like figure things out. Okay, yeah, all right. So we will continue from here tomorrow. So any further questions also, we will discuss them tomorrow. Yes. Fine.
Thank you, sir. Thank you so much.
Thank you, sir.
Thank you, sir.
Bye.
-2, -4.
Thank you so much.